On Earth, impossible is just an engineering brief. In humanity's most unreal megaprojects across the globe, trains soar nearly 360 meters over the Chenab River, bridges conquer valleys deeper than most skyscrapers, and tunnels pierce 57 kilometers beneath the Alps. These aren't fantasies, they're record-shattering solutions that stretch steel, concrete, and physics to their limits. But how do you knit continents together with cables and laser-guided drills? The answer's rewrite what you think is possible. Steel, concrete, and wind shape the world's most ambitious bridges, each one a laboratory for the limits of physics. In eastern China, the Danyang Kunshan Grand Bridge stretches for 164.8 kilometers, carrying high-speed trains across floodplains, rice paddies, and the Yangcheng Lake. Over 9,500 piers, set in rhythm like piano keys, lift the viaduct above shifting soils and wetlands. Modular construction lets crews slot in deck segments day after day, while seismic dampers and deep pile foundations anchor the structure against earthquakes and typhoon surges. But when the gap is too wide for repetition, engineers turn to cables. The Akashi Kaikyo Bridge in Japan spans 1,991 meters across the Akashi Strait. Its main cables, spun from enough wire to circle the Earth several times, are shielded by 4 layers of galvanization, wax, and polyethylene. In 1995, the Kobe earthquake shifted one tower nearly a meter overnight. Satoshi Kashima, the project's chief engineer, faced a decision that would define his career: recalibrate the cable sag and tower geometry in real time or risk collapse. He chose adaptation. The final deck, a streamlined box girder, was shaped in wind tunnels to cut through typhoon gusts and resist the kind of resonance that once doomed the Tacoma Narrows. Fiber optic sensors now live inside the cables, sending live data on tension and corrosion to inspectors who can intervene before disaster strikes. In southern France, the Millau Viaduct floats above the Tarn Valley on masts 343 meters tall, taller than the Eiffel Tower. Its deck, a multi-box girder, was honed by wind tunnel tests to flex, not fight, the wind. Slender piers, founded on 38-meter deep piles, allow the bridge to ride out storms with tuned mass dampers and live strain monitoring. China's Duge Bridge, perched 565 meters over a canyon, holds the record for the highest road deck on Earth. Engineers used double-wall box girders and bundled cable stays, tested against 200 km/h winds, then anchored into bedrock with gravity blocks and rock bolts. Inclinometers and GPS sensors track every millimeter of movement, ensuring stability above the clouds. Each of these bridges is more than a path between 2 points. They are experiments in stretching steel, taming wind, and outsmarting gravity. At their heart is a relentless process of testing, monitoring, and learning, led by engineers who know that a bridge's real strength is measured not just in tons of steel, but in its ability to adapt to the unexpected. Deep beneath the Swiss Alps, the Gotthard Base Tunnel slices through 57 kilometers of bedrock, longer than the Channel Tunnel and deeper than most skyscrapers are tall. Crews spent 17 years carving 2 parallel tubes, working under nearly 2,000 meters of mountain. Temperatures soared above 40 degrees Celsius. Tunnel director Marcus Weiss called the greatest challenge cooling the mountain itself. 4 tunnel boring machines, each the length of a football field, chewed through hard gneiss and unpredictable squeezing zones, sometimes advancing only centimeters a day. Laser alignment kept the 2 ends on course, with the final breakthrough missing by less than 5 millimeters. Ventilation systems blasted cool air to the front lines, while emergency shafts and hundreds of cross passages provided escape routes for crews facing sudden rock bursts or floods. In 2011, a cooling system failure trapped 17 miners for 9 hours, an ordeal that tested every safety protocol the team had built. Emerging from the tunnel, the world's fastest trains race across continents. Japan's Shinkansen is a lesson in discipline and precision. Bullet trains reach up to 320 km/h, yet average less than 30 seconds of delay per year. The rail operations chief credits a culture of punctuality that drills every staff member, from drivers to platform cleaners, in synchronized routines. Seismic sensors line the tracks. If an earthquake is detected, power cuts instantly and trains brake to a stop. The Shanghai maglev, floating on a cushion of magnetism, hits 431 km per hour on its short airport run. No wheels, just electromagnetic force keeping the car levitating millimeters above the guideway. Engineers monitor every joint and coil for heat and vibration, keeping the system in balance at speeds that rival a jet on approach. Japan's next leap, the Chuo Shinkansen maglev, aims for 500 km per hour, tunneling under the Southern Alps for most of its route. Over 80% of this new line will run underground, with vacuum-sealed tunnels and pressure-controlled cabins to keep passengers comfortable as they cross mountains faster than most planes. These networks, both above and below ground, rely on relentless accuracy, millimeter tolerances, real-time data, and a mindset that treats every second and every degree as critical. On the upper Yangtze, concrete and water collide at a scale that bends imagination. The Three Gorges Dam stretches more than 2 kilometers across the river, rising 181 meters high, its bulk locking in a reservoir that snakes for over 600 kilometers upstream. Deep inside, 32 turbines spin out a combined 22,500 megawatts, enough to power entire provinces. But size is only the beginning. The world's largest ship elevator, nearly 100 meters tall, lifts vessels the height of a skyscraper in a single, counterweighted chamber, a vertical shortcut that slashes hours off river journeys for cargo ships too massive for the 5-stage lock. Yet the real challenge is not just holding back the river, but keeping it alive. Every summer, the Yangtze surges with silt, threatening to choke turbines and raise the riverbed. At the heart of the dam's control room, the systems manager tracks sediment levels like a doctor reading vital signs. When the time comes, bottom sluice gates roar open, flushing millions of tons of mud and sand downstream in a controlled pulse. It's a delicate balance, too little, and the reservoir fills with silt. Too much, and downstream farms and cities risk flooding. Further west, the Baihetan Dam pushes arch design to new heights. Its double-curved concrete wall, nearly 300 meters tall, channels the Jinsha's force into granite cliffs. 16 giant turbines, each 1,000 megawatts, hum beneath the surface, cooled by water drawn from deep in the reservoir. Here, silt management is a team effort. High-velocity outlets at the base blast sediment out during peak flows, while a network of downstream dams catches what escapes. Downriver on the Yellow River, Xiaolangdi's engineers face a river so muddy it's called China's sorrow. Their answer? Let the dam breathe. Each summer, water levels drop and silt tunnels open wide, sending a brown surge racing toward the sea. In a good year, up to 800 million tons of sediment clear out, an engineered exhale that keeps the river from rising and the turbines from grinding to a halt. The systems manager describes it as a negotiation. Power, flood safety, and a living river all pulling in different directions. Every decision is a trade, measured in megawatts, tons of silt, and the pulse of water that connects mountain to sea. Nearly 2,700 kilometers of canals and tunnels now move the Yangtze's water north, reshaping China's geography. The South, North Water Transfer Project, relies on pumps so large they could power small cities, lifting water in stages, sometimes 23 times along a single route. Regional planners weigh each decision. Sending water north means less for southern farms and wetlands. Over 300,000 people were relocated, entire towns rebuilt on higher ground to clear the canal's path. For the planners, the work is a constant negotiation between supply, demand, and the human cost of redirection. Tokyo's Jikan system faces the opposite problem: sudden floods. 5 shafts, each deeper than a 15-story building, stand ready to swallow rivers when typhoons hit. Water surges through tunnels wide enough for trucks, gathering in a vast underground chamber lined with 59 concrete pillars. 4 jet turbine pumps, each matching a locomotive's horsepower, can move 200 cubic meters per second into the Edo River. Every summer, the system is tested by downpours that once brought the city to a halt. Since Jikans began, flood losses have halved, but planners warn that climate extremes are pushing the system to its limits. In the Netherlands, the Maeslandkering barrier guards Rotterdam. Twin steel gates, each the length of a football field, swing shut when North Sea storms threaten, sealing off the port. Ball joints 10 meters across anchor the gates, inspected for fatigue cracks after every closure. A coastal defense engineer describes the annual ritual: ultrasonic scans, pressure tests, lubrication. The barrier has closed only 28 times in over 25 years, but each closure is a reminder. Millions of lives and Europe's busiest port depend on its strength. Dubai's deep tunnel. Stormwater system takes a different approach, racing water out to sea. Pumps move 40 cubic meters per second through a 10-meter wide tunnel monitored for cracks and settlement. Here, maintenance is a race against time, because one failure could turn highways into rivers. Where the land runs out, engineers invent new ground. The Hong Kong-Zhuhai-Macau Bridge stretches 55 kilometers across the Pearl River Delta, a chain of viaducts, artificial islands, and an immersed tunnel that disappears beneath the shipping lanes. In 2014, a sudden rush of water flooded the undersea tunnel. A coastal megasystem engineer, still haunted by that day, describes the scramble. Divers sealed leaks with concrete bags, while giant pumps fought to hold the line. The incident forced a redesign of every segment seal and rewrote the safety playbook for the rest of the project. Today, the bridge tunnel carries tens of thousands of vehicles daily, its joints and pressure sensors checked with the vigilance of a submarine crew. On Singapore's western edge, the Tuas megaport rises from land that didn't exist a decade ago. Reclamation here means more than just piling up sand. Automated stacking cranes glide across the world's largest container yard, tracking every box by GPS. Algorithms choreograph the movement of ships and trucks, squeezing maximum throughput from every square meter. Beneath the surface, engineers monitor for ground settlement, adjusting fill, re-leveling tracks, and injecting grout to keep the port flat as it grows. Every few years, teams review sensor data and recalibrate, knowing that even a few centimeters of tilt can jam the automated yard. Osaka's Kansai International Airport floats on a man-made island surrounded by seawalls and anchored to seabed piles. Yet the weight of runways and terminals pushes the ground down year after year. Maintenance crews inject concrete beneath the foundations, raising sunken sections back to level. The airport's survival depends on this cycle: predict, measure, correct, turning crisis management into routine. Across these sites, the boundary between land and sea is never settled. For coastal engineers, stability is a moving target, and the only constant is adaptation. Glass, steel, and concrete reach for the clouds in a new kind of arms race, one where height, spectacle, and digital skin redefine the skyline. In Dubai, the Burj Khalifa rises 828 meters above the desert, its Y-shaped core and staggered setbacks breaking the wind into harmless eddies. During construction, a single concrete pour climbed 600 meters in a 32-hour marathon, with teams scrambling to clear a jammed pump line before the mix set solid. The project's lead engineer still recalls improvising with ice slurries and custom blends to keep the pour alive. In Kuala Lumpur, Merdeka, 118's triangulated glass facade twists 679 meters above the old stadium, its sharp edges channeling typhoon winds down the structure. The architect behind its shimmering skin calls it a fusion of tradition and tech, each panel angled for stiffness, light, and a nod to the city's past. Shenzhen's Ping An Finance Center cuts wind loads by nearly half with its aerodynamic taper. Tuned mass dampers, giant steel weights, sway inside the crown, calming the tower when storms roll in. But vertical ambition isn't just about height. India's Statue of Unity stands 182 meters tall, assembled from 2,000 bronze panels, each mapped by GPS to fit the contours of a national hero. In Las Vegas, the Sphere turns architecture into a media event. Its 112-meter dome is wrapped in a programmable LED shell, the world's largest digital canvas. Across Singapore's skyline, the Raffles City Crystal floats 250 meters up, a 12,000-ton sky bridge linking 4 towers. Below, the rain vortex at Jewel Changi Airport drops water 40 meters through a glass funnel, its pulses and light shows choreographed by computer. For these megaprojects, engineering and art collide. Towers become wind-tuned sculptures. Buildings double as instruments, screens, and symbols, each one pushing the limits of what a city can be. 400 kilometers above Earth, the International Space Station circles the globe every 90 minutes. Its assembly demanded more than 40 launches, with modules crafted on 3 continents, each tested for the smallest flaw. Astronauts rely on welds X-rayed for hidden cracks, seals pressed to perfection because a single mistake can't be fixed from the ground. The ISS is a living experiment. Its systems upgraded in orbit, every repair a high-stakes gamble. Farther out, the James Webb Space Telescope sits 1.5 million kilometers away, beyond the reach of rescue. Its gold mirror, folded tight for launch, had to unfold flawlessly in the cold of space. Cryogenic cooling chills its sensors to just above absolute zero, letting it catch the faintest glow from the universe's first stars. For the deployment scientist, there was no backup plan. 107 release mechanisms all had to work, or decades of hope would vanish. Beneath the French-Swiss border, the Large Hadron Collider forms a 27-kilometer ring, cooled by 120 tons of liquid helium. Protons race at nearly light speed, guided by magnets so precise that a weld out of tolerance or a magnet misaligned by a millimeter can halt the world's most powerful experiment. In southern France, ITER tries to bottle a star, fusing hydrogen at 150 million degrees. Every weld on its vacuum vessel is a potential failure point. Across South Africa and Australia, the square-kilometer array listens for signals from the dawn of time. Its antennas stretched across continents, fighting interference from cell phones and satellites. Here, ambition is measured in microns and megawatts, but fragility is the true test. Before steel and concrete, ancient builders set standards that still test the limits of modern engineering. The Great Pyramid at Giza, assembled from over 2 million limestone and granite blocks, stands with its base aligned to true north within a fraction of a degree. Each side deviates by less than 4 centimeters across 230 meters, a precision achieved with sighting rods, ropes, and the stars. Some blocks, weighing up to 15 tons, came from quarries as far as Aswan, floated down the Nile during its annual flood. The Great Wall of China stretches more than 21,000 kilometers, crossing mountains and deserts. Ming-era builders fired bricks on site, shaped the wall to the land, and raised watchtowers wide enough for marching columns and signal fires. The wall's scale and endurance speak to a vision that spanned centuries. In Cambodia, Angkor's engineers built a city of water. Vast reservoirs, canals, and moats channeled monsoon floods, irrigating fields and cooling temples. LiDAR scans reveal a hidden network of embankments and ponds beneath the jungle, exposing a metropolis shaped by hydraulic mastery. High in the Andes, Sacsayhuaman's limestone blocks, some weighing 125 tons, fit together without mortar. Their jigsaw pattern and sloped faces let the walls withstand earthquakes that toppled later structures. At Baalbek in Lebanon, the Temple of Jupiter's podium rests on stones weighing up to 800 tons. These megaliths, cut and set with millimeter accuracy, were moved with levers, sledges, and sheer determination. Each monument stands as a silent challenge. With simple tools and collective will, their makers achieved what many still struggle to explain, leaving questions that echo through every new ambition. From the Danyang, Kunshan Grand Bridge, stretching 164.8 kilometers, to the Great Wall's 21,000-kilometer span, humanity's largest projects have reshaped land, water, and even the boundaries of knowledge. Records show that the Gotthard Base Tunnel required over 2,400 workers and 28 million tons of excavated rock, while the Three Gorges Dam displaced more than 1.3 million people. Yet, despite detailed construction logs and engineering blueprints, the precise methods behind some ancient feats, like the Great Pyramid's sub-centimeter alignment, remain unresolved. Today, official reports confirm that several megastructures face mounting maintenance costs and carbon footprints, and the long-term impacts of mass relocation and ecological change are still under study. Across eras, one fact stands: every megaproject is a record of both ambition and consequence. As engineers and societies commit to future builds, The archived evidence reminds us that true progress weighs innovation against its lasting footprint.